I have 10:15, so I'm going to go ahead and get started. Good morning. We have the mic on? Good. Good morning, everybody. I'm Rick Fienberg, AAS Press Officer. Very good to see so many people here bright and early on day 2 of this 227th meeting of the American Astronomical Society in Kissimmee, Florida. We have 4 very interesting results to be presented today, this morning. And I just want to remind everybody, make a few brief announcements and remind everybody how this works. So first of all, I want to remind our press registrants that if you managed to get a badge without a ribbon, please come see me in the press office after the briefing and I'll give you a little press ribbon. More importantly, we have a press reception this evening at 5:30 hosted by the American Institute of Physics, who are going to be presenting their Science Communication Awards right here in this room. So 5:30 for all press registrants here in this room. And then the most important announcement concerns the press dinner, which follows the press reception. The important part about the press dinner is that we're going to a restaurant of which there are 5 different versions in the area. And last night, I was in a car going to this restaurant for another purpose, and we started off going to the wrong one. So there's a map and directions to the press dinner in front of the mail office. If you're signed up to come to the press dinner, please look at the map or find someone with a car, and there are instructions for how we're going to get there on the sheet. Okay, the final announcement is just a reminder to silence your beeping devices, your cell phones and otherwise. We've put out, there's been at least one press release that's went out for this morning, and there's, I believe, 1, possibly 2 more coming. So you can look for those in your inboxes after the briefing. Okay, so this morning's briefing is one very provocative result on the search for life in the universe, followed by 3 presentations with new results from 4 different space telescopes. So, as always, we'll hear from the 4 presenters in order, and then we'll do questions at the end. So we'll start with Roseanne Stefano from the Harvard-Smithsonian Center for Astrophysics, whose presentation is entitled Globular Clusters as Cradles of Life and Advanced Civilizations. She'll be followed by Jim Fuller from California Institute of Technology, Caltech, on the asteroseismic signature of strong magnetic fields in Nature just a couple days ago, and will be in this week's print issue. He'll be followed by Rubab Khan from NASA's Goddard Space Flight Center on Hubble and Spitzer finding stars similar to Eta Carinae in other galaxies. We've had several Eta Carinae-focused press conferences over the years. And finally, Husheng Nayeri from the University of California at Irvine on Herschel's discovery of gravitationally lensed dusty star-forming galaxies. And that does not refer to John or William Herschel, but to the European Space Agency's Herschel Space Observatory. All right, and with that, I will turn it over to Roseanne. And it looks like...
I'm Roseanne Stefano, and today I would like to talk with you about what it might be like to live in a globular cluster. Globular clusters, whoops, you've gone one too far. Globular clusters are old. There are 150 of them in the Milky Way, and they tend to be about 12 billion years old. They're dense. Central densities range from about 1,000 to 1,000,000 stars per cubic parsec. Now, these clusters are so old that the most massive stars, the only low-mass, long-lived stars that die very gently. So, in a way, it would be very serene to live in a globular cluster, but it would also be bright because there would be so many nearby stars. So, let's see, I seem to have skipped something. There we go. To compare with the solar neighborhood, where our nearest star is Proxima Centauri, about 1.3 parsecs away, if we lived in a globular cluster, the nearest star might be only 1,000 AU away. And if that's in light, might take on the order of a month rather than 8.6 years. And any travel that we wanted to do to that star would take 1/100th the time it takes to go to Proxima Centauri. So Alok and I started talking about a globular cluster opportunity. that the very old stable populations, coupled with the very small distances between stars, might make it possible for civilizations in globular clusters to travel and possibly to develop outposts at relatively short times. A catastrophic event would destroy the situation, become smaller. Do globular clusters have planets? Well, these stars are old. They were formed at a time when there were few heavy elements that are needed for planet formation. However, the Kepler space mission has established that low-mass stars with low metallicity often are orbited by Earth-sized planets in the star's zone of habitability. That zone of habitability is where water can exist on a planet like the Earth, on the surface of the planet. And for low-mass stars like those in globular clusters, the zones of habitability are closer to the star because the stars are less luminous. And that's a good thing, because the proximity to other stars not only allows you possibly to travel to them, but it makes those stars close enough that they may travel toward us and interact with us and perhaps eject planets from our planetary system. Smaller planetary systems have a better chance of surviving for a long time. In the upper panel, we plot the log of the survival time for planets in the habitable zone versus the log of the distance from the center of the cluster. And that very high top curve tells us that a 0.1 solar mass star in this particular globular cluster, which we modeled, could survive for more than 10 to the 10 years, even at the center. The 0.8 solar mass star, represented by the curve below, would not survive, its planets in the habitable zone might not survive over very long times until you get further out in the cluster. However, once it's there, the second panel shows us that interstellar distances, here we're looking at the log of the distance in terms of AU, would be only a few thousand AU, and that's good. Now, moving out toward the edge of the cluster, stellar distances increase, and by the time you get to where they're about, maybe 10 to the 4 AU between typical nearest neighbors, we might say the globular cluster advantage is no longer so important. So the region between these two lines, this is the region that we have referred to as the globular cluster's sweet spot. In this region, which is a large annulus, stars can survive, or planetary systems in the habitable zones of stars can survive, and yet it's dense enough that it may facilitate interstellar travel. So it behooves us to ask, how many communicating civilizations could there be in globular clusters? By this we mean advanced civilizations that might communicate across interstellar distances. We don't know the answer, but the Drake equation provides a way for us to compare globular clusters to the galaxy, where we know of one communicating civilization. And if the two factors on your right are the same in the two environments, which we'll assume for now, the number of communicating civilizations scales with the number of stars in each environment. I'll spare you the math, but suffice it to say that if 100,000 communicating civilizations formed at some point in the history of the Milky Way, then each globular cluster would have a chance, very likely, to have had one communicating civilization formed within it. If that is the case, and if this civilization was able to establish outposts, then globular clusters may indeed contain very old advanced civilizations. Which clusters should we look at first? Well, we did a study where we compared planets in the habitable zone to recycled pulsars in globular clusters and came up with an ordered list. I'd like to end simply by saying that our results indicate that globular clusters are good places to search for planets and for life. We have established the existence of these sweet spots, and possibly, if there are civilizations in those sweet spots, they would have the opportunity, this is going wild, they would have the opportunity to establish outposts that would facilitate their long-term survival. Thank you.
Good morning, everybody. My name is Jim Fuller. I'm a postdoc at Caltech. It's a great pleasure to tell you that today, for the first time, we have the ability to map the demographics of magnetic fields inside of stars, and we do this using astroseismology. I should say this is work led by Dennis Stello at the University of Sydney and Matteo Cantiello at University of California, Santa Barbara, and it was published in Nature just yesterday. Now, the reason this is exciting is that we've known for a very long time that magnetic fields can have a profound influence on the way stars live, the way they evolve, and the way they die. But we've had very, very few observational constraints about what kinds of magnetic fields are actually present. We learn about these magnetic fields using astroseismology. So the way this works is you just measure the brightness of a star very, very precisely for a very long period of time. We can do this with the Kepler Space Telescope, which is best known for finding planets around stars, but because it just is measuring the brightness of stars, it can also detect minute pulsations from these stars. And those pulsations tell you something about what the star is made of, how massive it is, how big it is. You can basically think of the star as a big pipe organ, and it's pulsating musical spectrum. And by measuring the amplitude of those different notes that it's playing, you can figure out what's going on inside of the star. So what I've shown here is the pulsation spectrum. It's basically just a Fourier transform of the brightness of the star. On the top panel, you see a normal star. I should say everything I'm going to talk about in this talk is a red giant star. So these are stars similar to the sun that have burned all the hydrogen in their cores, are now burning hydrogen in a shell around their core, and they've expanded to become more luminous stars called red. Several different notes. We understand the spectrum quite well. You can see that some of the most prominent features in this spectrum are the red colored regions. Those are called dipole modes. But what's interesting is that there are a separate class of stars where those red regions, those dipole modes, have much lower amplitudes. It's like those notes are somehow getting muffled. For some reason, something is preventing the star from playing those notes. And so what we showed in a paper published last year in Science is that a magnetic field can produce this effect, and so we can equate these stars and magnetic fields deep down inside of their cores. Okay, so what we've done now is to go ahead and make this measurement for thousands of stars in the Kepler field. And you can see in this plot that when you make this measurement of dipole mode visibility, the stars separate out very clearly into two classes of stars. There's the stars on the top branch, which are the normal stars, which have normal dipole mode visibilities, and the stars on the bottom half of the plot, which are the magnetic stars and have highly suppressed dipole mode visibilities. You can also lie, so the theory is matching up very well with the data. Now, the magnetic fields that you need to do this, I said, are localized inside the core of the star. You can't see them at the surface. But inside of the star, those magnetic fields can be over 1 million times stronger than a typical refrigerator magnet. So these are pretty strong fields. And you can see that they're present in a lot of these stars. And so when you actually crunch the numbers, figure out how many stars show this effect, the results are quite astounding. It turns out roughly 25% of stars show this effect, but that incidence function of the mass of the star. So this is the most important result of the paper. What we've plotted here is a histogram of the fraction of stars that have these strong magnetic fields as a function of their mass. And you see that in low mass stars, roughly 1 solar mass, you essentially never see this effect. It's very rare. But in stars that are a little bit more massive, about 1.5 solar masses or greater, you see that this effect is very common. It occurs in roughly half of those stars. So it looks like these strong magnetic fields are very common in stars slightly more massive than the Sun. Now, the mass at which this bifurcation occurs is roughly 1.1, 1.2 solar masses, and that corresponds to the point at which these stars, during most of their life, either have or do not have a convective core. Okay, so a star like the Sun does not have a convective core. That means deep down inside of the Sun, there are no bulk fluid motions of the star, whereas in stars slightly more massive, you have these bulk fluid motions that are carrying nuclear-generated energy out from the core of the star. And we think it's those convective that are responsible for generating the magnetic fields inside of the slightly more massive stars. So this has been seen in simulations. Here's a very nice magnetohydrodynamical simulation by Kyle Augustin, which shows that you can generate these magnetic fields in the convective cores of stars this way. So it looks like this effect, which had only been sort of theoretically speculated about, is actually very, very common inside of slightly more massive stars than the Sun. The other implication is that stars like the Sun do not have strong magnetic fields in their cores. This, inside of the descendants of Sun-like stars, it appears that our own Sun probably does not have a very strong magnetic field in its core. The other implications are that magnetic fields, have been neglected in stellar evolution for a long time. And now we see that they're common and they can be very strong. It can have a very important influence on stellar evolution and need to now be incorporated into stellar models so that we can understand them better. And finally, these magnetic fields can have an extremely important influence on what happens to the star when it dies and after it dies. We see very strong magnetic fields in the corpses of stars. It looks like some of those magnetic fields may be the descendants of the ones that we're discovering inside of red giants. So only time will tell if that's the case. And finally, I should say, we haven't been able to perform this measurement for the most massive stars, but those are the stars that go supernova or create things like gamma ray bursts at the end of their life. We know magnetic fields can be important for those events, and it looks like the magnetic fields could be common in those stars as well. We don't know for sure, but that's the implication here. So I will leave it at that. Thank you.
All right, thank you, everyone. I'm Rubab Khan from NASA Goddard Space Research Center, and today I'm happy to tell you about our discovery of 5 stars in nearby galaxies that are similar to the galactic superstar Eta Carinae. Now, Eta Carinae is one of the true superstars of our galaxy. It is one of the most massive and most luminous stars within 10,000 light years. It is more than 100 times the mass of our Sun and more than 5 million times more luminous than our Sun. In the 1840s, Eta Carinae had a giant eruption that threw up more than 10 times the mass of our Sun into space. Now, that mass formed dust into it, as we see in this